In the following public lecture on exceptional harmful algal blooms and their apparent association with unusual climatic conditions in New Zealand, Dr. Hoe Chang, Emeritus Scientist from the National Institute of Water and Atmospheric Research, shares his expertise on toxins and the toxicology of algae and cyanobacteria. He also discusses his latest research findings on toxic and noxious microalgae in relation to the climatic conditions in New Zealand.
In this morning's presentation, I will focus on exceptional harmful algal blooms and their apparent association with unusual climatic conditions in New Zealand. As you can see, this is a joint presentation with the colleagues, Dr. Brett Mullen from the National Institute of Water and Atmospheric Research in New Zealand. We'll first look at what exceptional blooms are and then move on to look at unusual climatic conditions, El Nino Southern Oscillation or ENSO, Interdecadal Pacific Oscillation, IPO, their impacts on New Zealand, exceptional harmful algal blooms or HABs in New Zealand from 1950 to 2016, long-distance transport of HABs, and then conclusions. So what are exceptional blooms? Exceptional blooms are defined by ICES, or International Council for the Exploration of the Sea. It's defined in 1984 as those which are noticeable, particularly to the general public, directly or indirectly, through their effects such as visible discoloration of the water, foam production, fish or invertebrate mortality or toxicity to humans. And these are some examples of visible surface discoloration caused by extensive Nautilus scintillans blooms in both nearshore and offshore waters around New Zealand. You actually see very spectacular bioluminescent effects of this picture. It was actually taken from a website in Google. And this is our research vessel, Tangura, and we encounter a very spectacular Nautilus blooms on one of our cruises. This is in the oceanic waters. And this was surface foam production reported in the 1998 Marine Life Kills events in Wellington Harbour. This, in fact, was an unprecedented bloom. Pretty much everything in the harbour died, including seaweeds. You'll be surprised that this toxic events also kill seaweeds. These are some human toxicity reported by major newspapers in New Zealand. The 1992-1993 shellfish poisonings such as NSP, PSP, DSP, and ASP, and also outbreaks of human respiratory distress on the northeast coast of North Island, New Zealand. Another thing I should mention, this NSP outbreaks was the first time ever that actually happens in New Zealand, and also the first NSP outbreak outside the east coast of the United States. In this presentation, we only focus on mainly those exceptional harmful algal blooms that were reported for the period from 1950 to 2016 in New Zealand. This period was pretty much when I started my job at the National Institute of Water and Atmospheric Research, and previously it was called New Zealand Oceanographic Institute. So I started in 1978 to last year, so sort of encountered quite a lot of this bloom during this period of time. Before looking at all the exceptional HABs that were reported from that period from 1950 to 2016, I I would like to go through with you very quickly the unusual climatic conditions New Zealand experienced and their impacts over that period. The first unusual climatic condition that I'd like you to look at is this El Nino Southern Oscillation, or ENSO. So what is it? In fact, this is a Pacific-wide phenomenon which oscillates 2 to 7 years. But in the case of New Zealand, we pretty much experience either El Nino or La Nina every 2 to 3 years rather than 2 to 7. It is associated with strengthening or weakening of the westward equatorial trade winds. In normal condition, the westward equatorial trade winds sort of push surface warm water from the east to the West Pacific. This arrow actually shows where the westward equatorial trade wind moves. So it becomes warmer in the west than in the East Pacific. La Nina is an intense version of the normal condition. So strengthening of this westward equatorial trade winds cause more surface warm water to be pushed across from the east to the West Pacific. So it gets much warmer in the west than in the East Pacific. So this is what La Nina condition is like. Vice versa, El Nino, that's associated with the weakenings of the westward equatorial trade winds. So during El Nino, you actually see less warm surface water to be pushed across from the east to the West Pacific. So it becomes a little bit cooler in the west than in the East Pacific. These are sea temperature differences from average in both El Nino and in La Nina conditions. In El Nino, typically it is cold all around the West Pacific. You can see blue marks cold water and red marks warm water. So including New Zealand, in fact, they were actually sort of bathed in cold water on the West Pacific. And you also see a tongue of warm water sitting on the equatorial East Pacific. La Nina is the opposite. Typically, it's warm over the West Pacific, around the West Pacific, including New Zealand. I hope that you can see it here, with a tongue of cold water sitting on the equatorial East Pacific, which is here. So this is quite a good contrast. So how does ENSO typically affect New Zealand? These are wind anomalies around New Zealand in typical El Nino and La Nina conditions. In El Nino, typically New Zealand experiences more frequent and stronger southwesterly wind. So it sort of moves from here to here. So that is southwesterly wind. Much of the country is affected by this southwesterly wind, and also more frequent and stronger northwesterly winds on the northeast coast of New Zealand. La Nina is the opposite. Typically, New Zealand experience more frequent and stronger northeasterly winds, just the opposite. It comes down from the north. And also more frequent and stronger southeasterly winds on the northeast coast of New Zealand. How does ENSO impact on sea surface temperature in New Zealand? As you can see, these are sea surface temperature anomaly found around New Zealand. Blue marks cold water and red marks warm water in both El Nino and La Nina conditions. In El Nino, typically strengthening of both south and north westerly winds leads to increases of upwelling and surface deep mixing, and thus results in cool surface water all around New Zealand. So you could see lots of cold water surrounding New Zealand in El Nino condition. In La Nina, typically, strengthening of north and southeasterly winds leads to downwelling, the opposite, and results in stable and warm surface waters all around New Zealand. Impacts of ENSO on surface coral reef A, as you can see here, these are satellite ocean color images showing the general distributions of coral reef A marked in red around New Zealand. This is in El Nino condition, and this is in La Nina. In El Nino, strengthening of either southwesterly winds around the South Island Cape Farewell or the northwesterly wind around the North Island northeast coast, which is somewhere around here, leads to increases of outwelling and surface nutrient enrichment, which in turn leads to substantial increases of coral reef A in those two main outwelling areas. So you could see plenty of very strong coral reef A build up in those two outwelling regions as marked with arrows here. And the reverse is true for La Nina. Strengthening of the north and southeasterly winds in the two corresponding regions leads to increases of downwelling. It's not upwelling, it's downwelling, which in turn leads to drastic declines in coral reef A. You don't actually see much coral reef A here in La Nina compared with the coral reef A that you could actually pick up during the El Nino in these two main upwelling areas. Now let's take a look of another unusual weather condition or climatic condition that is known to impact on New Zealand, the interdecadal Pacific oxidation, or what we call IPO. This is similar to that of Pacific decadal oxidation, or PDO, but because IPO is defined for the whole Pacific basin rather than just for the North Pacific, so IPO is used here in preference to the PDO. So I'll keep on using the term IPO rather than PDO. The primary effects of IPO are on the ocean temperature. And as you can see, there are two phases, the warm positive phase and the cool negative phase. In warm positive phase, it is warmer than normal over much of the East Pacific, while in the cool negative phase, the reverse is true. It is normal or cooler than normal over the East Pacific, but much warmer on the West Pacific. And each IPO phase lasts 20 to 30 years, unlike ENSO, which oscillate every 2 to 7 years, or in New Zealand case, from our records, it's every 2 to 3 years. Impacts of IPO on ENSO. This is a plot of IPO index versus years from 1950 to roughly 2016. As you can see from this period from 1950 to 2016, New Zealand experienced two periods, these two periods here marked in blue, with negative IPO indexes, and one period with positive indexes from 1979 to 1998. Blue marks the cool negative phase, and red marks the warm positive phase. This is a plot of Southern Oscillation Index, or SOI, versus the same period from 1950 to 2016. Negative IPO phase, which are these two here, tends to be associated with strong La Nina. You can see it here, very high peaks, and with relatively weak El Ninos, and vice versa. Positive IPO phase, which is this one, tends to be associated with strong El Niños and with weak La Nina. So all this red actually marks La Nina events and blue El Nino. Now let's take a look at occurrences of all exceptional HAB or harmful algal blooms that have been reported or recorded from 1950 to 2016 in New Zealand. The first period from 1950 to 1978 that I like you to look at is actually a co-negative IPO phase, which is this one here, negative IPO phase. The first 4 outbreaks in 1955, 1962, 1964, and 1966 reported in this co-negative phase were actually all slime outbreaks. They occurred in La Nina and were found in close embayment in Nelson, South Island, which is around here. These slime outbreaks were probably associated with the dinoflagellates called Goniolex hyalina. I'll come back to talk a little bit more about it later. The second exceptional blooms reported in 1978, again in the co-negative IPO phase, was caused by Prorocentrum micans, which is this one here. This bloom occurred in an El Nino event, which is this one here. The previous 4 outbreaks all occurred in La Nina. They were very well spread on the west coast of South Island, which is around here. Prorocentrum micans form high biomass blooms. Collapse of these high biomass blooms can cause anoxia and potentially could also cause fish kills, particularly in the close embayment. When the blooms die off, it sort of depletes or the dissolved oxygen in a closed embayment, and so would cause fish kills. To recap for the first period, from 1950 to 1978, the first period of cool IPO phase, we actually see 4 slime outbreaks and 1 algal event. And now we'll move on to the second period. From 1979 to 1998, this in fact is a warm positive IPO phase, which is characterized by strong El Nino with relatively weak La Nina. The first outbreak in 1981-82 in a warm positive phase was caused by this Goniolex hyalina. These blooms occurred in a La Nina events, which is this red pig here, and they were confined to a closed embayment, again just like the previous 4 slime outbreaks in Nelson, South Island. Goniolex hyalina also forms high biomass blooms, and it was found to produce massive amount of slime, both in culture and in the field. Slime outbreak was reported to clog fishing nets and possibly also fish kills, so potentially it can cause fish kills. This is likely to be the same as those 4 previous outbreaks reported in the cool negative phase. Of course, there are other algal species that could cause slime outbreaks as well, like some of the Cossinodiscus and things like that. But because all these slime outbreaks occurred in Nelson, and also really thick slime has actually been reported in the same area, so we are saying that maybe all the previous 4 events are pretty much like this one here. The 1981-82 outbreaks, the species was actually sort of correctly identified and cultures been made. So we could actually see that this bloom, in fact, was related to this species. The second harmful HAB reported in 1983, also in the warm positive IPO phase, was caused by two species, Salatorina pelagica, a Dalton, and Prorocentrum carathiferum, a dinoflagellates. These blooms occurred during a very strong El Nino event. As you can see, the SOI, the Southern Oxidation Index, is close to -3. This, in fact, is the strongest among all these El Nino events in the last 66 years. This bloom were very well spread on the northeast coast of North Island, New Zealand. Salatorina, again, forms high biomass blooms. Prorocentrum carathiferum, which is this one here, is a new species described by Chang and Ryan in 1985. And this species, in fact, has also been implicated to be hemolytic. So they cause fish kills around this region in the 1983 outbreaks. The third exceptional HAB reported in 1986 in the warm positive IPO phase was caused by Amphidinium carterae. This bloom occurred in an El Nino event, which is this one. They were very well spread on the northeast coast of North Island, which is around here. Amphidinium did not cause any fish kill on this occasion in 1986, but is known to be hemolytic. The fourth exceptional HAB reported in 1989, also in a warm positive IPO phase, was caused by this species, Heterosigma akashiwo. This bloom occurred in La Nina, which is this one here. This bloom was actually found in Big Rory Bay at the southern tips of South Island. And they caused massive salmon kills in the fish farms. Actually, over 80% of salmon kept in the farms were killed by these exceptional outbreaks. Heterosigma akashiwo has been implicated as hemolytic. The fifth exceptional outbreaks in 1992-93, in fact, were multi-species harmful algal blooms. Several species were involved in these harmful outbreaks. This bloom occurred in 1992-93, which pretty much around here, during a prolonged El Nino event. As you can see, there were 3 El Ninos in a row from 1992 to 1994. They were very well spread on the northeast coast of North Island, New Zealand. The multi-species blooms included 3 new Karenia species. The first one, a Karenia spur, later described as Karenia concordia. I'll talk a little bit more about this later. And 2 other Karenia species, K. pepperinaceae, which is this one here, and K. bidigitata. Both were described as new species by Haywood and others in 2004. Other toxic species involved in this bloom were Alexandrium minutum, which are these 2 cells here, and Dinophysis acuminata pseudonesia australis. During this outbreak, while over 100 people were reported to suffer from NSP and PSP all around the northeast coast of North Island, and over 300 people were reported to experience human respiratory distress. This involved with dry coughing, and also some people reported to have skin rashes if they went to swim in the sea. So this were pretty nasty kind of blooms. And I think one of the species here, Karenia concordia, in fact, was the culprits. During this period, DSP and ASP toxins were also detected in shellfish. Shellfish harvest in New Zealand over the whole period of this really nasty outbreaks were banned for almost 6 months, so nobody was allowed to take or consume shellfish in the 1992-93 outbreaks. The 6th exceptional HAB reported in 1994 in a warm positive IPO phase was caused by Karenia selliformis, and this bloom occurred in 1994 at the end of the 3 consecutive El Nino events from 1992 to 1994. So you could see all these 3 El Nino periods we had toxic outbreaks of many species. These outbreaks or blooms were very well spread and were found along the east coast of South Island, New Zealand. They caused massive marine life kills. Karenia is a new species. This one here is a new species described by Haywood and others in 2004. Potent toxin produced by this species is gymnodimin. The blooms lasted for about 3 months. The 7th or the last exceptional blooms reported in 1998, also in the warm positive phase, was caused by Karenia brevisaucata. This bloom occurred during an El Nino event. They were very well spread in both Wellington Harbour here, I don't know whether you can see it, and also along the northeast and east coast of North Island, New Zealand. They cause massive marine life kills and again human respiratory distress. So in New Zealand we actually had 2 Karenia spur or species that could cause human respiratory distress. Karenia brevisaucata, which is this one here, is a new species described by Chang in 1999. Toxins produced by this species are brevisaucata toxins, or what we call KBTX, and 18 different toxin derivatives were actually identified from the culture of this species here. If you take a look of this satellite ocean color image here, you could see a very strong chlorophyll build-up on the east coast of New Zealand. Actually, this was the area where human respiratory distress was reported in 1998. So we had hundreds of cases of human respiratory distress reported around this region in New Zealand. To recap, this warm positive phase, as many as 7 algal events and 5 new species, and most marine life kills and human toxicity were actually reported in this warm positive IPO phase. Now let's move on to look at the IPO phase from 1999 to 2016. This is a co-negative IPO phase. The first outbreak reported in 1999 in this negative IPO phase was caused again by Gonerax hyalina. This bloom occurred in La Nina, which is this one here, and were found in a close embayment again in Nelson of South Island. Gonerax hyalina, like in previous occasions, all the other outbreaks in the first period of cool negative IPO phase and one in the warm positive IPO phase, they were all associated with slime outbreaks. The second exceptional HAB reported in 2000 in this co-negative IPO phase was caused by Gymnodium catenatum, which is this one here. This bloom occurred in a La Nina, which is marked in green here, and they were very well spread along both the west coast and east coast of North Island, New Zealand. Gymnodium catenatum has actually been identified as a PSP producer. There were a few cases of human PSP outbreaks along this part of the North Island, but because this species has already been identified as PSP producer, so people were warned not to consume shellfish from the affected area, so there wasn't really very many cases of PSP during the time. The third exceptional HAB reported in 2002 in this second Q-negative IPO phase was caused by Karenia concordia. This bloom occurred in an El Nino event, not like the two previous events, around the Hauraki Gulf on the northeast coast of North Island, New Zealand. This is a satellite chlorophyll A image showing a very strong buildup of chlorophyll A, marked in red here. And this bloom caused marine life kills as well, since it's one of the Karenia spur, which are very well known to cause marine life kills in New Zealand. Karenia concordia was reported here as a new species by Chang and Ryan in 2004, pretty much like the previous outbreaks in 1992-93. At that time, we only named that as Karenia spur, but later on, we found out that, in fact, it was the same species as this one, which is Karenia concordia, and it's named as Concordia because of its shape. Pretty much looks like a Concorde aircraft. The fourth exceptional HAB reported in 2010, in fact, were multi-species harmful algal blooms. They occurred in an El Nino event, which is this one here, and they were found in Wellington Harbour in the North Island, and also Marlborough Sound in South Island. This multi-species bloom included 4 species: Heterosigma akashiwo, which is this one, Pseudochatonera verruculosa, and also Karenia concordia and Vicistus globosus. These outbreaks caused fish kills in fish farms and also in the field. To recap, for the second Q-negative phase, you can see 1 slime outbreaks and 3 harmful algal events, plus 1 new species reported for the whole period. In the last 66 years, from 1950 to 2016, a total of 8 exceptional HABs were reported to spread hundreds of kilometers along the coastline of New Zealand. So these are all the 8 exceptional HABs that were known to have a long-distance transport. 7 out of these 8 exceptional blooms, if you look carefully, actually occurred in El Nino, and only 1 occurred in La Nina. And 5 of these exceptional blooms, this one, 1, 2, 3, 4, and 5, reported during that period from 1950 to 2016, were all reported during the warm IPO phase. So only 2 were reported in the 2 cool periods. So the bulk of the exceptional blooms actually occurred during the warm IPO phase rather than the cool periods. And virtually all 7 of these long-distance along-shore transport of exceptional HABs were associated with 4 major currents around New Zealand. The East Auckland currents here, Wairarapa currents around the North Island, and 2 around the South Island, Westland and Southland currents. Again, if you look carefully here, 1, 2, 3, and 4 of these exceptional blooms, in fact, were reported to occurred on the northeast coast, and in fact, that they were associated with the East Auckland current. So 4 out of 7 were associated with just one current alone on the northeast coast. And the remaining three, which are these three, 1, 2, 3, were associated with three different currents. This one here on the northwest coast was associated with western current, and this one was associated with the southern current, and the last one here with Wairarapa current. The 2000 PSP or Gymnodinium catenatum bloom was the only exception, which did not appear to associate with any current, especially on the west coast of North Island. Since there isn't a proper current on the west coast of North Island, so the spread of this Gymnodinium catenatum blooms, in fact, was probably wind-driven, not actually sort of driven by the current. In conclusion, most of the exceptional HABs over the last 66 years reported from 1950 to 2016 in New Zealand were reported in the El Niños, with a few in La Niñas. The close coupling in timing of exceptional HABs and ENSO indicates strong linkages between such harmful algal events and the unusual weather patterns or climatic conditions. Most exceptional HABs or harmful algal blooms were recorded in the warm positive phase from 1979 to 1998, characterized by strong El Niño with relatively weak La Niña. Actually, a total of 7 harmful events, 5 new species, and most marine life kills and human toxicity were actually reported in this warm positive phase. Less frequent HAB events, however, were reported in the 2 cool negative IPO phases, there's 2 here, from 1950 to 1978, and from 1999 to 2016, both characterized by strong La Niña and with relatively weak El Niño. A total of 4 slime outbreaks and exceptional blooms were reported in the first cool period, and 1 slime and 3 harmful algal events plus 1 new species were reported in the cool negative IPO phase. So you could see quite a bit of difference between the cool and the warm IPO phase. With 2 exceptions, virtually all exceptional outbreaks reported in the strong La Niñas. Here in the 2 cold negative and 1 positive phase were all slime outbreaks except these 2, marked in green. So pretty much La Niña is associated with slime outbreaks. The largest number and variety of exceptional HABs observed in the warm positive IPO phase in New Zealand are suggested to be associated with the strengthening of El Niño, which in turn lead to increases in the intensity of upwelling and surface nutrient enrichment during this period. Cold negative IPO phase, however, appears to be associated with the strengthening of the relatively calm and warm conditions in La Niña, which in most cases is known to shut down upwelling. Apparently, the major long-distance alongshore transport of exceptional HABs are associated with the major currents around New Zealand. As I mentioned previously, the 4 major currents are East Auckland current, Wairarapa current around the North Islands, and the 2 western and southern currents around the South Island. Lastly, I'd like you to take a look at this IPO index plot again. Don't know whether you could see it. There is a tiny red dot here under the green arrow. It looks like the negative IPO indexes actually ended in 2016 and then sort of shifted to a positive index in 2017. At this point, we are not sure whether this positive index will stay on like this or not. If it did stay on from now on, are we going to see another very strong El Nino with many exceptional harmful algal blooms like the warm positive phase that we actually saw from 1979 to 1998? I think it's quite possible if it did actually sort of stay on like this, and only time could tell. I'll end this talk here. Thank you very much for your attention.